All right, let's jump straight into this explainer. Today, we're tracking the incredible journey of water, starting all the way from global, big picture systems right down to the precise environmental engineering it takes to actually get it to our taps. We're going to explore exactly where our water comes from, how the Earth acts as this massive natural filter, and the honestly brilliant ways engineers have figured out how to capture it. But first, we have to start with a pretty shocking reality. Just take a look at this number. Out of all the fresh water on Earth, a tiny 0.26% is actually economically accessible for human use. Think about that for a second. We literally live on a blue planet, yet the vast majority of that water is locked up in oceans as saltwater, frozen solid in glaciers, or trapped way too deep underground for us to reach. This incredibly tiny fraction makes water one of our most precious resources. And it's exactly why mastering the engineering of our water sources is absolutely crucial right now. So, here is our roadmap for today. 1. Earth's vital water sources. 2. The science of infiltration. 3. Factors affecting infiltration. 4. Engineering infiltration galleries. 5. Engineering infiltration wells. And finally, 6. Formulas for yield and capacity. Section 1. Earth's vital water sources. This gives us a great look at the classic, unending hydrologic cycle. As you know, it all starts with precipitation, rain and snow fall down, running off into our streams and rivers. But here's the crucial part. A really significant portion of that water infiltrates the soil. It percolates downward to become the utilizable groundwater that makes up so much of our accessible supply. It's a great reminder that water is never truly stagnant, right? It's always in constant circulation. Now, what's really fascinating here is the stark contrast between our two main sources of supply. Over on the left, you've got surface water. Your rivers, your lakes, these are super easy to see and access, but they are highly prone to pollution. Then, on the right, we have underground sources. These rely entirely on the Earth's natural filtration system. And because of that, the resulting water is bacterially much safer and incredibly clear, making it a highly desirable target for environmental engineers. Section 2. The science of infiltration. Okay, to really master this, we need to nail down two specific terms, infiltration and percolation. Infiltration is the actual physical passage of water crossing the soil surface to fill up the voids, those little empty spaces within the dirt. Percolation is what happens immediately after that. It's gravity doing its thing, pulling that water further and further downward until it hits the water table. Think of the underground aquifer kind of like a bank account. Rainfall is your income, and infiltration is that essential deposit mechanism safely putting your water into the soil's vault. Section 3. Factors affecting infiltration. But of course, nature doesn't just give us a constant, steady rate of deposit into our groundwater bank. The whole system is highly variable. As you can see, there are 8 major factors dictating infiltration capacity. It's a real mix of physics and human action. For instance, a coarse-grained soil texture really increases infiltration, while a high groundwater table just blocks it entirely. Heavy rainfall intensity can actually pack the soil down and reduce infiltration, whereas a lighter, steady rain increases it. And temperature, believe it or not, cold water is more viscous, so it moves slower. Plus, human activity, like paving our roads and building out cities, severely cuts down the Earth's natural capacity to absorb all this water. Because those factors vary so wildly, engineers have to physically measure infiltration capacity out in the field. And to do that, they use this, the double-ring infiltrometer. See, if you just pour water into a single tube, it's going to escape sideways into the dry soil, right? That gives you a completely inaccurate, artificially high reading. The absolute genius of the double ring is that the outer ring acts as a constant 5-centimeter water jacket. It essentially forces the water in that inner measuring ring to travel straight down, which perfectly simulates natural rainfall conditions. Section 4. Engineering infiltration galleries. Meet the infiltration gallery. When a surface river is heavily polluted or just really turbid, an infiltration gallery acts as this massive, horizontal, porous barrel buried right into the riverbank, usually at pretty shallow depths of about 3 to 5 meters. So instead of pulling dirty water straight out of the river, engineers use the sandy, gravelly soil of the riverbank itself as a natural, large-scale filter to extract that clean subsoil flow. Now, conversely, what if a horizontal gallery just isn't viable because of the local geology? Well, that's where engineers utilize infiltration wells. These are vertical structures that intersect deeper, pervious layers. They're basically used to abstract much larger, deeper supplies of groundwater, taking full advantage of those aquifers located way beneath the surface. Let's actually bounce back to the gallery for a second to see how this subsurface extraction physically operates. Because the step-by-step process shows the pure elegance of this design. First, the river water naturally percolates down through a specially prepared gravel and sand bed. Second, this newly filtered water enters loose-jointed or perforated pipes. And finally, because those pipes are laid on a slight gradient, the clean water just flows horizontally right into a main collecting sump well, where it can be safely pumped out. You get all the volume of the river, but with the cleanliness of groundwater. It's brilliant. Section 5. Engineering infiltration wells. Bringing back that bank account analogy for a minute. If rainfall is the income and infiltration is the deposit, pumping from these deep infiltration wells acts as our direct, engineered withdrawal from the aquifer bank. And the success of this withdrawal heavily depends on the geological formation's porosity and its permeability. Basically, the Earth's ability to actually transmit the water to the well. If we pump too fast, we overdraw the account. And that leads to dry wells and collapsing soils. Section 6. Formulas for yield and capacity. To make sure we don't overdraw our water account, environmental engineers can't just guess. They absolutely rely on some precise mathematical formulas. Looking at these syllabus-critical equations, we can easily see the actual mechanics of water extraction. Darcy's law is the bedrock here, telling us that flow, represented by Q, equals the soil's permeability, K, multiplied by the hydraulic gradient, I, and the cross-sectional area, A. We also have the W index, which really refines how we calculate infiltration by taking total precipitation and subtracting runoff and storage over time. And finally, specific capacity tells us exactly how much yield a well gives us per unit of depression head. These equations are the literal key that allows engineers to calculate precisely how much water and infiltration work can safely produce without destroying the aquifer. Now, I want to leave you all with a pretty provocative thought. We just looked at the precise math governing our water supply, right? But those formulas fundamentally rely on inputs like precipitation and rainfall intensity. So as changing climates radically alter those variables, bringing heavier, faster storms that actually decrease natural infiltration, how is the next generation of engineers going to have to completely redesign our entire approach to capturing and storing water? It's a massive challenge, and it's one that will absolutely define the future of that precious 0.26%.